Welcome everyone to this seminar today. This is part of a seminar series of our NASA Sala 4 ULI project. So it's a great pleasure today. We're hosting the talk by Dr. J. Wilhelm. Dr. J. Wilhelm is an associate professor of mechanical engineering at Ohio University, and he holds a PhD in mechanical engineering and a master and bachelor degrees in electrical engineering, both from West Virginia University. So he works with Avionics Engineering Center and the Ohio Research Institute for Transportation and the Environment. And his research expertise is in autonomous systems for ground and aerial systems, autonomous driving experiments, and advanced air mobility. He also works on collision avoidance, design and evaluation of intelligent systems, and position accuracy and integrity trust impacts. Dr. Wilhelm has received several grants over the last 10 years from the Ohio Department of Transportation, the U.S. Department of Transportation, FAA, U.S. Air Force Research Lab, U.S. Army Air Force Research Lab, Ohio Federal Research Network, and the National Science Foundation. And I know Dr. Wilhelm is also co-PI of one NASA ULI project. So please join me in welcoming Dr. Wilhelm. The stage is yours.
Thanks, Ever. I really appreciate that. So this is what I'm going to overview here. I'm just going to give a brief, little more detailed introduction about myself. I will talk about the Rust College to sort of set the stage for what goes on here. The Avionics Center, my research lab, a little bit about self-driving vehicles, and then some AAM related projects. And please, if you have any questions throughout this thing, let me know. I can see the chat as well. So like Dr. Moncayo said, I'm an associate professor in mechanical engineering at Ohio University, but I'm also part of the electrical engineering and computer science department as well. So I graduate MS students from there in the past. Just like Dr. Moncayo, I went to school at West Virginia University to get my PhD. To answer your question from earlier, yeah, I go back there once a year because I'm on the advisory board for the Lane Department of Computer Science, Electrical Engineering. We participate in their, ABET review processes with them. And then this year they elected me to their Academy of Distinguished Alumni. So I got to go back and be a part of that. And it's interesting because that Academy has, the inventor of the cable modem, a very famous individual from Oracle software. And then at the very, very bottom of the list is me, just university professor here. After finishing my PhD at WVU, I stayed there for 5 years as research assistant professor. And that's an interesting role where you have freedom to do things and acquire grants. And that's what I was doing and performing research, but no credit towards tenure. So, I was searching and ended up at Ohio University. My main overall, thread between all of these projects that I've ever had is something to do with autonomy or intelligence or automating something. I mean, I'm a trained controls engineer. So the Rust College of Engineering at Ohio University, we're your typical engineering school with mechanical, civil, chemical, industrial systems, electrical engineering, computer science, and then there's some new ones with energy and environmental in there, and then there's a technology program. We call it Engineering Technology and Management. And then our computer science program branched out a little bit and just started AI and cyber undergraduate degrees, which is pretty interesting. And there's a lot of new focus on semiconductor work because of the Intel facility that's being built outside Columbus, which is about an hour and a half drive from where we're at. They realize there's nobody in the state that really can train workforce. to build semiconductors. So they reached into the university programs across the state to help bolster that. 1,700 undergrads right now to give a size of the college. And, we have about 100 PhD students on average over the years. Something like 98% of our students end up getting a job, the undergraduates, after they finish their degree within 6 months. So that's really good placement right now. Of course, those numbers could change. There are a bunch of research centers, one on corrosion, avionics, transportation, and then sprinkled throughout some other ones on energy and the environment and some other smaller things. But really, there's 4 large centers that most of the faculty do their research through. There's also an aviation engineering program, and I wanted to throw this in here because I know Embry-Riddle does this as well, really training pilots over a 4-year program. Really awesome system they've got set up, and thanks to Maj, the 6 Cirrus SR-20 aircraft showed up this year to inject into that training program because they were using 172s and Pipers from a long time ago. So that's really great. They're using super modern equipment. They have their own hangar for storage facility and maintenance hangar as well. And they operate out of our airport. And so really the aviation program and the avionics center are the only things at the airport. Sometimes people bring in, private planes and land there, but it's very seldom. So, and then the Avionics Engineering Center, 60 years ago was founded. And our airport, of course, at the university was a completely different location. It was moved in the 70s. But they have done a ton of work on radio navigation, in terms of like instrument landing system, VOR, and distance measuring equipment, that kind of work there. That's continuing today because the FAA about 15 years ago thought they were going to turn all that off. They're kind of expensive to maintain, and then GPS was coming in, and everybody thought, you don't need radio beacons anymore. But then now we know GPS can be jammed relatively easily if you have enough power. So they're going back to these things. The problem is that it's been 30 years since one of them has been installed, and in terms of VOR DME. And so if you open up the box on one of these things, as I've done, the electronics in it is older than anything I understand, and we wouldn't build them like that today. So they're kind of redoing what the requirements and the designs look like to make sure that equipment is maintained through the years and new installations are possible. Again, it's at the university airport, so there's a row of 3 hangars, and the avionics center has their own, as you kind of see in that upper left picture there. And I'll talk about what the airplanes are in a second. But this is a foundational place that's very well known. In the 2010 timeframe, they actually had enough funds to make their own small building that's at the airport as well. It houses office and labs and storage space. And so the avionics staff ended up moving there. There's it fluctuates between 10 and 15 people usually that are part of that center, full-time research staff. But these people have done great work, and the FAA continually calls and asks them to do.
Hey Jay, you went muted.
Man,
Good.
how did I get muted?
Just 5 seconds ago.
Okay, that's crazy. Not that I clicked anything. Yeah, let me know if that happens again. Sorry.
Of course.
So this avionics center has 4 aircraft right now. There used to be more in the systems over the years. The big one is the DC-3 from 1943. That was actually used in World War II as a Army cargo aircraft, and then after the war was converted to passenger status. And there's a huge plug over the cargo door, which is really neat. And then the FAA used it. They had a fleet of hundreds of these that they would fly around to various airports and do inspections. And then in the 90s, these are kind of falling out of favor. and they donated 3 of them to the university. One of them was scrapped. Supposedly, one of them is buried on site somewhere, and the other one is still flying. So we have a lot of parts for these things. The one that's really fun to fly is the King Air C-90. This is a pressurized aircraft. You know, much higher altitude. You can't go above 10,000 feet in the DC-3 unless you want to put on oxygen. But the King Air, sometimes we use that for travel to go to places like visit the FAA. Comfortable plane. The Piper Saratoga and Beechcraft Baron there, you know, they're the back seats are basically taken out, and there's racks in there, and all 3 or 4 of these aircraft have various different ports and antennas for mounting whatever specialized power that's available for whatever payload you need, and then a separate GPS receiver and data feed just for that, so that when payloads are put in there, you know, we're not plugging into the plane's systems or avionics. It's completely separate. So a lot of the time, people bring payloads to be tested to the university, and we're working with a handful of companies right now that have things that they want flown. And all 4 of these aircraft, I think they're all rated experimental right now because of the antenna ports, but they go back and forth sometimes. Sometimes we put the seats back in and take the experimental rating away. Just a couple, you know, good projects to try and boast about the center. That NASA project, I'll go into some detail about that in a minute. I talked about the VOR DME program. There's a joint university program that's been sponsored by the FAA for 50 years now. It's in collaboration with MIT right now. There's only 2 universities, but Princeton used to be involved. I can't really point at another, you know, small university that has a 50-year-old program that we compete with MIT. So we're bumping heads with them with, you know, various different tasks come down from that program to train graduate students. So they have a really good time with that, and you know, those students have won a lot of awards. The CubeSat went up in 2020. That was a good one to really look at GNSS data. And you know, there are receiver networks across the world, but now we have one on top of our engineering building that was receiving data just from that. And the PI on that, I think, is planning to do another payload. And then there's a low altitude weather monitoring project that went on a couple years ago that was funded by the state. And this was to you know, make an inexpensive little weather monitoring box that could tell you like cloud coverage, you know, temperature, wind speeds, a bunch of other different things for less than 400 feet, specifically for, you know, drones and AAM. So this is my lab here that I call Ideas. You know, it's an indoor motion cap flight space that we set up, and I do a bunch of, you know, either guidance planning type work with the motion capture system, or alternative positioning solutions. So you can use that as a ground truth. So it's neat to close the loop from sensing to guidance, then back to control commands to flying quadcopters. And I think I've had like 5 or 6 of these little like crazy flies in the air at the same time going around. And then we operate some fixed wing aircraft as well. And then in 2022, I got a Chrysler Pacifica that's self-driving, and I'll talk about that project in a minute. But this is space that gives the students a chance to explore, you know, what it takes to do experimental flight indoors, which is not easy. And we also work on jet engines in here too. So we have, I think I have 5 P100s and 2 P300s from JetCat. And so we're part of an Air Force project that every year they give us different requirements for a capstone experimental design process. And so the students have to do a bunch of research on how to, you know, do the modifications, what they need to design around, and then they modify the engine and test it. And so far we've been taking it outside and running it. So real quick, I talked about our automated driving project a little bit earlier. So In 2019, I think we started collaborating with the Ohio DOT and the US DOT about what it would take to drive in Appalachia of Southeast Ohio. And so I pulled these three routes up right here, and they're a very hilly region. It's very, very up and down and very windy, and probably the most difficult place we could think to drive an autonomous vehicle. We think about, big cities and people everywhere, but that has been nailed down pretty well. Going to a rural environment is a little more challenging. So I use that self-driving van that I acquired to get moving on this project, and we brought in the Transportation Research Center as well. That's up in Marysville, Ohio, which is like west of Columbus, and that's a test track that was made for Honda, and has since gone to a private company that they call TRC. And so we did some controlled testing there, where we set up scenarios, and they had vehicles that they were driving, and then we brought it down to Southeast Ohio, and picked these three routes, had them mapped, and drove. I think it was like 3,000 miles. Most of this was through like 2-lane roads in the back areas where there's not a lot of traffic, but we did go through uptown Athens. We went through a bunch of stoplights, and we found out a lot of different things, and it was challenging at best to figure out how to evaluate how autonomy isn't seeing the world. And so for perspective here, I pulled this map of the United States, and dot down where we're located and where we tested, because I know most of you guys are probably in Florida right now. And Appalachia, is really core from, I'd say like northern Alabama, like up to New York, and we're not in the worst of it here, but we're in typical conditions for this region. For sure, Ever and I experienced West Virginia University and the crazy roads there, but that was leaning a little more towards urban. But the rural areas are all real similar. So our goal was, we wanted to collect a bunch of data about how open source autonomy stacks would work under these conditions. So we have a vehicle with LiDAR on top. This one's a VOP32. So we got 32 lasers going around. There's a radar system on the front. And so the bluish bars in the circular are the LiDAR, fuse in the radar with the little green stacks. There's 2 cameras looking forward, and we have differential GPS with RTK. So we can get 1 to 2 centimeters of accuracy, and we need that to make sure that we're driving on the road correctly. For the most part, these systems use the GPS, not the line striping to stay in the lane. You need to know where you are anyways, so they pushed it to work with GPS mainly. And then that vehicle I'm using, it has electric power steering, an actuator already in the brakes for safety purposes. The throttle is electronic as well, because it's a plug-in hybrid. You have to have that. And then the gear can be actuated. It's like a little turn knob thing, so it's completely electronic. So because of all that, I can stop somewhere, put it in park, and engage our autonomy system, and then it completely handles all functions of the car. It even does the steering wheel or the turn signals. When we come up to road intersections, we indicate which way we're going to turn with those turn signals, which is more than I can say for most of the population. So I always like to show this. This is a data capture that I got fairly early on with this vehicle, because this is the data feed that it's working with, and I visualize it for a human. But the vehicles don't see like we do at all. Once you add this LiDAR point cloud generation, you have a completely different view of the world. And it's kind of challenging to computation wise to take a point cloud feed like this, and like we can identify that there's like cars and other vehicles, but the processing algorithms have to figure out, is that a car, is it a person, what the trajectory is, where is that going to impact where I'm trying to drive, because I have a route that I want to go, I know where the road is. So it's feeding a lot of information, and we had some problems where for sure there wasn't enough computation. In addition, it's also taking that video feed and trying to identify objects in there, and that was based on a graphics card, and all these things have limits. The more features you put in the world, the more complicated it is, the more difficult it becomes. So we had 330 times that we went out and drove to collect data. During that 3,300 miles, there were over 4,000 driver takeovers, and that was because there were a lot of instances early on where the car started to veer a little bit, and the driver would take over to deal with it and not go off the road, and then would re-engage, and then you would do that a mile or two later, and so there was an excessive amount of takeovers. We categorized each reason for the takeover, so the system, unlike what we would think, never automatically disengages on its own. It was always a driver or somebody in the back looking at the data feed saying, hey, you need to stop. So we call them takeovers instead of disengagements. But then we categorized them all, clustered them together, sort of looked at where we're going, and the path tracking is definitely the biggest challenge that we have. The unknown, I have no idea. Sometimes it wasn't logged. We kind of move on from that, but the stoplights were a huge issue too. Sometimes it didn't see it. Sometimes it saw crosswalk signs and had to disengage. That or just sat there at the stoplight. So even though you could see two green lights, this one red light overrode that, and so we never went anywhere. But overall, there are definitely some technology improvements, but I think those don't outweigh the need to always have access to excellent tracking, and this is like low GPS error. If your error, for whatever reason, you have access to less satellites, or the cell connection drops out so you can't get the corrections, if that's going on, then we have issues, and it's only a matter of time until we have to disengage. But this kind of wraps up that whole project. This is what we were looking for, to feed information back to the US DOT to say, hey, if you were going to focus on something, here's the numbered list of the things you need to focus on, which is, how do you make your infrastructure better to track roads? How can you standardize stoplights better? How do you improve road striping, things like that. So I'll move on now to the what I call practice. And so this is one of our collision avoidance algorithms that we came up with. And I had a really good time with this one because most of the work was done in March of April of 2020. That's when our project was going on, and that's the time that was set aside to really make the developments and define the requirements for this. But the world was kind of shut down during that time period. So I was able to do a lot of coding and dig pretty deep to this. There's not much else to do. So we were looking at, how do you provide a collision avoidance system that takes over control of a fully autonomous UAS. So no pilot interaction, whatever. So if you look back to manned systems, TCAS is required in all passenger aircraft over, I don't know, it's 20 passengers or something in the plane. And this requires these airplanes to communicate with each other, to share their positions, and a tau value is calculated that based on the trajectory of the aircraft, how long until a time to impact occurs, And then there's a heuristic set of rules to say if the tau value is this, you need to, in the path is going a certain way, you need to climb or turn left or descend or whatever. It's been very successful if the aircraft actually have them fully in it. Lots of collisions have been avoided over the years, but it doesn't scale down to small UAS. And I say that because if you're under 400 feet, you really can't climb or descend. You really have altitude restrictions. You want to keep flying at the altitude you're at. So we want to turn left and right, but in TCAS, it pushes you off your heading, and that's fine if you have somebody monitoring and piloting the aircraft. You get pushed off your heading by 20 degrees, or you have to climb 1,500 feet per minute. At some point, the pilot realizes that you're clear of conflict, and then you can resume path. But if you're automating it, none of this is there. So we were inspired by TCAS and included its heuristics, but then went ahead and said, well, what if you had in front of you a conflict zone, and all the aircraft project this cone in front of them, and it's the 30-second worst case scenario. Where can you go? So obviously you can fly straight, you're still in the cone, or you turn left or turn right. That's based on your turn rate. That's how wide the cone is. And if those cones touch each other, there may be a collision. There's a chance for a collision there. So we projected those cones, and then if detect a collision of those, polygon and polygon type detection, very, very quick computation, and action is taken at that point. So we plan around where we're going, and then we override and execute, take over from the autopilot. And then the really neat thing is to recover back to the original path. So like I said, with TCAS, you're pushed off, but with this, you can come back. And the automation part of it is really where I stepped in. So sure, people have done the detect collision, plan around, but then there's not been much on the go back to the original path. You may go back and point to your waypoint that you're headed to, but not back to the original path. And I did this because most of these platforms are really used for surveillance. And so if you're surveying somewhere aerially, and you get pushed off and you go back to your waypoint that's next, it's definitely not going to be over where you want it to look. So I came up with a way of zooming back in. So here's an example of the two aircraft flying at each other. They hit that point where those cones touch, and then our aircraft on the left does a plan around it. And the plane part's fairly simple. In this case, there's no other keep out zones or things that we can't touch. We take the geometry of the world there, and then we convert it to an A-star grid. And the only keep out zone is that red triangle on the right. And each of those black dots is a possible place that you can go in the grid to segment the waypoints a little bit. And in this case, we are slightly higher or more higher in the one direction than the other direction. And the system chooses to turn left to get away from that plane. There's the impossible case of the planes are perfectly heading at each other, sometimes produce a singularity and don't go around, or randomness comes into play which way you're going to turn. That never actually happens in reality. You never have two aircraft perfectly flying at each other. So we always offset them a teeny tiny bit. So this is the first step or second step. First step detect, second step plan around. And then, once we're clear of the conflict, which is like our cones are no longer touching at all, or if we turn back to our original path, we're not going to intercept that cone. We do the path recovery part. And this is where I spent most of my time, was trying to figure out the most efficient way to get back on our path. And so I wanted to use clothoids so that we could take into account a position that we return to, but also be pointed in a very, very specific heading, which is along the path. So for sure, we could choose the shortest point and turn into the path, but that doesn't always guarantee that when we intercept the path that we're pointing in the right direction. So clothoids work great with that. The problem is clothoids don't always respect our turning radius capabilities. So sometimes it'll choose a route, or yeah, it'll choose a path for us that we can't actually fly. So I went through a whole optimization process to find that iteratively, um, and search the space. So that was the really the challenging part of this. And you can see from this figure here, like in the middle, that's where we want to actually fly. But there's some like purple ones. Yeah, they go backwards. But the one that is where you would think the closest intercept is, we couldn't actually fly it. So I'm checking that turning radius. And then we have some other ones that are acceptable in terms of the turning radius, but they're too long of a space. And then, through that process, we were looking at, the head-on. Well, what happens if you're perpendicular? So it turns out that this works really great for, let's say 60 degrees looking ahead. But if you get, to the perpendicular case, which is the worst one, our method for doing this tended to turn in front of the aircraft, and I don't think they were never going to collide, but turning in front of someone is terrifying, and nobody would ever agree to do that. So we wanted to turn behind the aircraft instead. So we looked at, how do we scale another keep out zone? When our cones touch, we basically extend the intruder uncooperative aircraft's cone just down the path there. So when A-Star plans, it's looking for the shortest path. It doesn't hit that cone; it goes around it. So I had a student, work through all the details of this, and then write a nice paper about it. But it was like another situation for practice, just to make it better and more usable. And then here I got a nice video that I created pretty early on of our system running. And say we wanted to run this like racetrack pattern, and we've got these three systems that are in the way. I'm going to automatically take over and turn back in. And this aircraft had a pretty wide turning radius. That racetrack pattern is about the maximum turning radius that it can do, or the best that it can do. And so I think it intercepts these aircraft 3 or 4 times, just because you've got two going across your path, and then one of them is really pesky and annoying and is turning directly into you. And so I ran simulations like this for quite a while, in a bunch of different cases, to explore like how well does it work. Really, we're trying to measure the cross track error and the time spent off of the desired track. Because if you think about, like, TCAS is only going to mess with your heading, and this one here gets you back on your track as soon as possible. So I think that's it. So I have tons and tons of videos like that. And then at the end of it, after about a year and a half of doing development work and simulations, we took it out and flight tested it. I was working with a company in Columbus that makes this autopilot. They call it Ironclad, which is based on PX4, and it's a embedded Linux system that they've called Ironclad because it's secure. So PX4 by default doesn't encrypt anything coming or going data wise, and so they needed more computation to be able to pull that off. And some other like safety things and verification on commands and things like that. But we were able to squeeze in our software, which was written completely in Python, into a Docker container running on this embedded computer system, which is tiny, and monitor an ADS-B feed of other vehicles. And then we had a connection to the PX4. So, they have a ground station, they upload the plan to the PX4, start executing it. Our system's running in the background. It's able to take command of the PX4, automatically upload the waypoints. They let me do this, which is bizarre. And then with no human intervention, uploads the waypoints, and then tells it to start executing, and then clear conflict, come back. So we did a flight test at this Darby Dan airport that's shut down airport. Nobody's using it. So we were able to fly fixed wing aircraft there. And then we had a multi-rotor copter that was flying towards it, at different altitudes, but we faked out the ADS-B data, changed it to make sure they were at the altitude. Doesn't matter in that case. It's only a 2D top-down type view. So the whole thing, worked as expected. It used our detection cones, planned a route, took over PX4, clear conflict, back on the route, and went about its flight. And so to me, that was a successful flight test. About 10 minutes after this happened, the airplane was loitering, and I don't know, something happened with the speed probe, and it crashed into the ground. And so they had some rebuilding to do. I was super excited, and the company that was operating the plane were kind of bummed out because they had some extra work. But all in all, excellent flight data that we got from it, and successful flight test. So I was real happy about that. And then a year and a half ago, we wrote a proposal for the NASA ULI, which is just like Dr. Moncayo did. But we were working with a company called Reliable Robotics out of San Diego. And we have a contact who is one of our graduates who got a EE degree here, and then was part of the Avionics Center. He's working on the positioning systems for their pilotless aircraft. And I show this Cessna Caravan here, a very strange picture. The engine's running. It's on the runway right there, but there's no people on board. And so they've done a bunch of flight tests where they've taken off, landed, flown in between, of course, with no pilot or any human interaction. It's completely autonomous. But they came to us with a problem of ground navigation precision and trust of your position calculation on the ground. It turns out that maybe the ground is not the most reliable positioning systems for aircraft. Once you get up in the air, it's perfectly fine. So they had a problem where they were not trusting their GPS feeds enough to navigate the taxiways. So right now, somebody has to manually use a control thing to move that aircraft to the actual runway. Once it's on the runway, it's great. In the air, it's great. Landing's great. But then they need somebody to take over and taxi it back. So they thought this is the next logical step of where to go. So we're looking at different ways of measuring that integrity or trust in the position solutions. And so one side of the project that I'm luckily not involved with is really focused on GPS and the inertial systems that go with that. And can things be improved there? How do you evaluate integrity for that? Luckily, GPS has been around a long time. A lot of people know the insides of it, and so they're jumping into the solution process and making innovations there. On my side, it's the non-GPS navigation, and so I have a method that we've been using for a while that I'll talk about in a minute. That is non-GPS position calculation using some sensors. And one of the things we started to do, we look a lot about like, here's how my position system works. Here's the error that I get with it. So we're adding in an integrity or quantitative evaluation of that calculation. So that can be used for the autonomous system to either stop operating or switch modes or alert an operator that a manual takeover needs to occur. And I'm not the PI on it, luckily. That's a lot of management stuff that is involved with that. But my colleague Sabrina here is, and we're with Virginia Tech Transportation Institute, Illinois Institute of Technology, Tufts, Stanford, and of course Reliable Robotics is in there. So we do some work with computer vision and are building out a way of looking at features or they're like contrasts of the image feed, and then evaluating like which of those features that are detected are real, should be used, should not be used. And then we look at each subsequent frame and we look at the vectors between them, and we can get odometry based on that. It will give us an incremental position calculation. And so, these are very mature algorithms that mostly work, but they don't always provide us that information about how much can you trust the solution. Even I'm guilty of this, of developing these systems, focusing a lot on how accurate it was, but not how trustworthy it can be. Those two things don't necessarily go hand in hand. So we're popping the lid open on some CV systems and looking at extracting some data from their processes to look at trust, and then we mess with the images. We make parts of them blurry. We purposely obstruct things to try and mess with that feature detection. And so far we've gone through and done some. This is an example actually from Flight Gear, a flight simulator program. And we're moving across in airport space and feeding that data to one of these computer vision systems, and playing around with like what happens when we change parameters inside the system, change the video feed. How did those feature detections impact the accuracy in the end, so that we have a number that we can attach to this to trust. So that's one of the parts of the ULI. The other one is this camera plus LiDAR hybrid localization. So about 5 years ago, we're messing with LiDAR systems. We have cameras everywhere, but we're using them separately, and so I wanted to combine them for a single localization solution. So what we did was placed a bunch of landmarks in a room, and we know their position. I'm using my motion capture system. We know our position because I can use that for truth reference. But we identify those landmarks visually using a camera. Then we range to them with the LiDAR, and then correlate the two together. And then using the known landmark locations, I can use trilateration to find my location. And this is sort of similar to how GPS works. GPS is really using what's called multilateration, which is like range to the satellites that's modified based on the atmosphere and relativity. The receivers know where the satellites are, but they're trying to calculate where you are, and it's really the intersection of a bunch of spheres. And so we use a numerical solver to do that, and we do that with trilateration as well. But what I figured was, these sensors are going to be present on autonomous systems anyways. Like, for example, Reliable Robotics is putting the LiDAR on their system now. They realize you need that for taxiing. They have cameras everywhere. So those things are already there. And so if you have that, you just need a little computation to be able to figure out where you are, if you know where things at an airport could be, measured for and classified as landmarks. I thought it was unique in the internal processes we were using. So we put forth an invention disclosure and just got the patent this year. So that, to me, that's a good thing. And of course, there's a bunch of papers, and I've got the references at the end of this. But how we started was simulating it in a program called AirSim that Microsoft makes. It's basically like a simulation environment for engineers that sits on top of the Unreal Engine, so we can move stuff around and know the positions of things and change stuff, and work with things like meters instead of whatever the heck Unreal uses for their distances. And there's like gravity involved. All this cool stuff is in there, but we're able to simulate a LiDAR real easy. And so we placed our landmarks as colored spheres, and fed the camera view into our system, combine the LiDAR data with that, because we calibrate our cameras. Of course, we have a projection matrix, and then do our calculations. So we're like, if we're looking forward, can we see these things, and then figure out where we are? And it worked, and it gave us like centimeter level error. And then we built it with actual camera and a LiDAR. We tagged everything with the motion capture system, so we know exactly where it is. We use color spheres because that was a super simple computer vision process to categorize it by color. It turns out that we're looking at this thing with spheres. Our LiDAR points have a couple scan lines across them, and so we matched what our known landmark shape was. Sphere, look at it any angle, it's going to be the same. To the LiDAR to figure out where the center was, because the center is where the landmark position is going to be. And our accuracy, like I said, stuck quite well to 1 to 2 centimeters when we did that. And then we started upgrading and moving along. So the Ouster OS1 has 128 lasers. So we started this with 16 lasers and moved to 128. It's a lot of data. But also looking at YOLO for recognizing the landmarks by, say, like a sign, like we've got grocer here and like the university logo and some other things. And that makes them unique. So we train on images in YOLO. We identify them visually, and then we range to them. And we know that they're flat, so we match the LiDAR to that. And then from that, we can figure out our position. And again, we get about the same accuracy, but completely changing what the landmarks look like. And then to fit this into that NASA project, we started looking at what are the markers inside our algorithm. And it turns out that the distances and the variance that we detect on the surface of the landmarks can be used to indicate what's going on. There's also a technique called ransack that's used for GPS that's looking at the ranging consistency. So over time, we're able to measure that. So we have these features now that we can like bubble up to the surface to say like, hey, these are how we can have confidence in our solution. So say we do things like mess with, you can only detect a part of the image, or our range is all over the place. For whatever reason, we get interference from the laser. We want to have a confidence of what our solution is generating. So of course, go back to the typical engineer, just make it work well. Okay, why isn't it working? How much can we trust this? So that's what we've been working on in this NASA project. And we've got a couple papers on some various techniques we're working with, like the computer vision side, and this one that will be at SciTech. We also go to the Institute of Navigation and talk about these things as well. It's at a conference called GNSS Plus. So that's all I got for now. Any questions or comments?
Well, thank you very much for such a nice presentation. I do have some questions, but I'm gonna just let the others to ask. So we're open to questions.
Hello, can you hear me?
Yes, go ahead, Kai.
Hi, this is Kyle. I'm at Embry-Riddle here in Daytona, but I'm from Ohio, from Akron, so it's cool to see what Ohio University is doing. I had some friends that went there, but I never really knew what was going on. But I had a few questions. I was wondering what you did a lot of work with the LiDAR systems, and I was wondering if you see the direction for autonomous cars and vehicles going LiDAR or camera, because you see Tesla and famously Elon Musk is like, LiDAR really doesn't have enough data, and I can understand that because you get way more data from a camera. I was wondering what your perspective is on that.
Oh yeah, I mean, great question. Because this is definitely a topic at the autonomous driving conferences I go to. For sure, LiDAR is the way to go. The camera is too easily fooled. And actually, when you take your camera and you want to do computer vision with it, the first thing you do is you drop the resolution down because it's too much data. But the 128 laser system is a lot of data. It's way more data than what the camera can do, and there's a lot of work going into like shape matching on the lidar, which is really challenging. And I don't know if you've ever seen the there was a box truck that somebody put the picture of a car on the side of, and the computer vision only system completely failed to realize that that was a truck. I thought it was a car. And,
Yeah, that's interesting.
but lidar will never have that problem.
Okay, so the down resolution is helpful in a way.
Yep. And to me,
Okay.
the biggest one is like always watch bio-inspired. So, our eyes range to things when we're looking at stuff. We do it and sometimes don't realize it. But if you only have one camera, you can't range to anything. So it's impossible to tell if that car is far away or close up.
Okay, that's cool. Yeah, I appreciate that. I can let some other people ask now.
And I'm sorry you're a Browns fan.
Oh, I'm from Cleveland, so you got to do what you got to do.
I might have to convert though, because Shador I think is going to light it up, and the Steelers are terrible.
Hey, if the rumors are true, we'll welcome you.
Hello, good morning. Thank you, Professor Wilhelm, and for the presentation, and to Professor Ever for his invitation. My name is Paulo Franco, and I am from the University of Antioquia in Colombia. And I have two questions. First one is about the autonomous vehicle, the self-driving car. You mentioned that you were driving it, for example, in rural ways. And I was wondering if, for example, all these rural ways were where they were asphalt ways, or if, for example, they were really bumpy. And I was kind of wondering this because of, for example, thinking about my country here in Colombia, rural ways, maybe they are not all asphalt. So if, for example, this particular element was considered for the speed management. And secondly, I wanted to ask about the A-star algorithm. I have worked, for example, here in this semester, I took uh, course which was about navigation precisely, and um, I used, for example, one of the problems that I found with A star was that it was only allowing me to move at 45 degrees. So other algorithms, like for example theta star and lazy theta star, they allowed more angles based on line of sight. So I wanted to ask, maybe if it was about computing required for the navigation algorithm, or if or if A star proved to be sufficient for the precas.
Yeah, sure. So the road wise, yeah, we drove on paved roads, but I would not say that they were of the greatest quality that anybody's ever seen. I'm sure, and especially Dr. Moncayo there in Florida, really good roads. But here and where we have the freeze thaw thing, it tends to break the roads apart. But nowhere near like gravel or dirt roads. Yeah, for sure. There's gonna be a serious problem with that. And I've already started to look at the gravel parts. How do we detect that we're even on a gravel road versus asphalt road? How do we change our driving parameters? And for sure, it's speed, and then how fast you want to turn. The completely different road conditions. So, but best of luck in Colombia as the road conditions continue to get below gravel to dirt. It's going to take a lot. And in fact, like you probably drive a completely different vehicle on paved roads versus dirt roads, right? You might drive like a Jeep or something in the dirt road, and you have a car that can handle the paved road, but you wouldn't switch the two. And then the other one about A-star, yeah. So computation was a huge concern for me when we started prototyping and doing our what happens after a replan is needed. I think the first cut it took 2 minutes to calculate that, which is crazy. But I got it down to it was like 200 milliseconds in the end by optimizing the grid of A-star. And you nailed it that like the grid is separated, so you really can't turn that much. But it turns out the aircraft can't turn that fast anyways, so that wasn't a problem. And for sure there are much better alternatives nowadays to A-Star, but every time you start adding more features and looking at different aspects, you start adding more and more computation to it. So I tried to stick with the most basic piece, and for what we're doing, 2D planning with aircraft, it worked great.
Oh yeah, thank you very much. Yeah, in my case, for example, I found like the same with A Star. It was like, I mean, the code, which is it was about finding the most optimal route between an area with between 2 points within an area with radar coverage. And with A Star, it was like quite fast. I mean, not it was not the shortest path, but it was the fastest. And with lazy theta, it was like similar. I mean, the time increased like 300% or something like that. So yeah, thank you very much.
Yeah. It's a good questions.
Any other question? I want to ask you, when you're talking about the detect and avoid system, and you were using the approach was using ADS-B data, right? Then if you have, I don't know if you went through some kind of risk analysis of what's going to happen when you have GPS problems, when you have GPS dropouts, or if you are flying in a urban environment or something like that, you may have shadowing or of the signal of the GPS. So I don't know how that propagates to the final localization of the vehicles.
Yep. And maybe you could see like the timeline of the work. I started with that collision avoidance stuff, had been doing a lot of path planning, in those two things, and then have really started to move over towards positioning and localization, because I know that that's a huge problem. So when we did our flight testing, the people I'm working with, they did a huge risk analysis on it, simulated the encounter more than I did, with messing with things, see what happens when GPS drops out, all that stuff. So we needed GPS to be fully functional on both vehicles for that to happen. But like I said, so the past like 2 years have really been into localization and positioning. So when I make some progress there, I intend to feed that integrity stuff back into the collision avoidance. So it's like, how much can we trust our solution? Does that impact the accuracy of where it's at? How does that feed into your planning?
Yeah. And I have seen some of the detect and avoid systems like the Cassia X, which
Yeah.
is using vision system, right? Like what you're doing with the localization using machine learning vision systems. So
Yep. And the big one, and I probably didn't talk about it, was ACAS X,
mhm.
which is a Markov decision process based. And I looked at it and said, can we implement this? And it's too burdensome. It's either a lot of computation that can't be done. They're really doing the computation beforehand, and they generate these massive, gigabytes upon gigabytes of table data that you look up. So you got to figure out where to store that and how to search through it. And it turns out that my simple solution is faster.
Okay. Well, that's why it's patent now.
But that ACAS X, you're gonna see it in, the FAA has really dug their claws into it, and has standardized the pieces around it.
Mm.
But they have never moved past like this implementation problem. It's been 5 or 6 years.
Yeah. No, that's great. Any other questions?
Well, however, I just also like to thank Jay for a great presentation, for its breadth and depth of topics that you covered. I see a lot of overlap of what you are doing, or complementary, I would say, overlap, but the work that we are doing at Embry-Riddle, and also a lot of complementary overlap with what Professor Ioana doing at his center, transportation center at USC. I think those two areas would be really fertile for collaboration between Ohio University, Embry-Riddle, and USC. And I encourage everybody to look into that. Thanks very much.
Yeah. Thank you. Thank you very much, Dr. Wilhelm, for such a nice presentation, and looking forward for discussing potential collaborations. Right.
Yep.
So,
We'll be able to do that at SciTech.
yeah, for sure. And if you have some time, we can bring you to campus, just 1 hour away, so we
I
can
would
plan
love
for
to.
it. All right. Thank you very much. And
All right.
thanks everyone for attending. We're gonna post this video, this presentation in the website of the project. So just look at it there. Thank you. Have a nice
Thank you.
day.
Thank you.
Have a
Thank
great
you.
day.
Jake. Thanks, everybody.
Goodbye. Thank you very much.
Thank you. Bye-bye.